Hi, I'm Jim Bates, Technical Services Director at Wells Manufacturing Corporation. Wells is a leader in the manufacturing and distribution of automotive electrical and wire and cable products. We at Wells recognize that today's automobiles are quite sophisticated and may be intimidating to a great number of people. But that's no reason to throw away your toolbox and stop working on these vehicles. Instead, we like to suggest you add Sure You Can to that toolbox. This new booklet from Wells is a simplified guide to finding and fixing problems found on late model automobiles. It contains information as basic as what hand tools you'll be needing and how to properly use them, to information on pulling service codes from the vehicle's engine performance computer. So come along as I join Scott Kuzy in performing step-by-step troubleshooting procedures and simple 2-minute tests on many of the vehicle's engine performance parts. After viewing this video and utilizing this guide, I know you'll agree that Sure You Can work on your vehicle's engine performance system.
Diagnosing and troubleshooting drivability problems on your vehicle doesn't have to be a mystery. And actually, replacing the component that failed is the easy part. The toughest part is deciding where to start. Hi, I'm Scott Kuzy, and along with me is Jim Bates from Wells Manufacturing as we take an inside look at diagnosing, troubleshooting, and repairing drivability problems on your vehicle. Now, Jim, a real basic place to start is with some hand tools.
That's right, Scott. The same type of tools you'd use around the home for any type of repair.
Sure.
But along with that, we're going to need some manuals. And we brought a couple along today. Now, this one is for a specific type of car.
Okay, and the nice thing about this is it has all the specifications in it that you need on your specific vehicle. So a manual like this is most likely going to be necessary during your diagnosis and troubleshooting.
That's right, Scott. And this one is basically how to use tools. Okay. How to use your basic tools, specialized tools, and it's got the step-by-step procedures that you're going to need at home to do some of the diagnostics you need for troubleshooting engine performance problems.
Certainly, and the best place to start is with both manuals. From there, you need a few specialty tools.
Here is something rather unique. It's a voltmeter, it's an ohm meter, a tachometer, a dwell meter. It's called a multimeter. And this is a real basic tool that you'll need to do a great number of repairs at home.
Certainly. Now, I want to note that it is a digital meter also, and that's what you're going to need because many of the test specifications are within hundreds of volts or even thousands of volts, so you're going to need that to be very accurate with your testing methods. Now, down here we've got a universal tester also.
Right, and some attachments that go along with it for specific applications. A universal tester such as this carries its own power supply. It has an indicator light that turns on and off to tell us when components are working or not working. It has color-coded clips so that we know just how to hook it up, and a very, very good manual that comes with this to tell us how to use it to test the various parts that we're going to be testing later on. And as I mentioned, the custom connectors that makes the job that much easier.
Sure. Some of the connectors that you have to probe into to test on the electronics of your vehicle are very small, very minute connections. The actual custom connectors like that make the job go a lot easier and a lot quicker. What else do we have?
Well, we've got a vacuum pump. This is a handheld vacuum supply. It can be used to pump up something that we want to test the vacuum chamber on and see if the component works or doesn't work as it responds to vacuum.
Certainly. And over there we've got a propane cylinder that many people are used to seeing right on a regular propane torch, but on the top of it is not a torch tip, is it?
No, we have a special valve that we use to administer propane into the engine through a vacuum port, and this will enrich in the mixture when we want to test something to see how it responds to a rich or a lean mixture.
Okay, very commonly used for testing oxygen sensors while the engine is running. And right over there.
Now, this is probably one of the most unique tools that we're going to be talking about today. Let me hand you this little key. That's called a code key. And this is what we use to put computers in diagnostic mode. Now, if you're lucky enough to have a late model car with a computer, you can actually use the vehicle's onboard computer to help you make the diagnostics that you need to do.
Exactly, and what we're going to use this key for is to plug it into the ALDL or ALCL connector. And what that stands for is assembly line communications link or assembly line data link. You'll use this tool along with what you're holding there, Jim, correct?
Right. Now this is another light, an LED, but this is a high impedance type of a device that's actually used so that the computer can blink out the trouble codes to us on cars that don't have an indicator on the dashboard. Now General Motors cars and Chrysler vehicles have a check engine light right on the dashboard that the computer will use to tell us what the trouble codes are. Now some Ford vehicles though don't have anything like that, so we have to supply a device that will give us the codes.
Okay, as a matter of fact right now why don't we step over to the car and we'll show you just how to extract those codes from the computer. Extracting the diagnostic codes from GM vehicles is actually one of the easiest to do, and you can do it from sitting right in the vehicle. But you're going to need just a couple items to do it with. First off, you need a pad and a pencil to write down the codes once you get them out of the vehicle. And you're also going to need the correct manual to be able to tell you what the code means once you've got it out of the vehicle, as well as the diagnostic chart that you'll need to begin service. Now there's two other keys that we have to have, isn't there, Jim?
That's right, Scott. The first one, of course, will be the one for the car itself, because we have to turn the ignition on to get the system operating. This, of course, will turn all of the dash lights on. And one of them in particular that we're going to be looking for is the service engine soon light.
Or that may appear as a check engine light on your vehicle. Either way, that's the light that we're going to watch. Now the other key we're going to need is not absolutely necessary. We could use a paper clip, but for our demonstration we're going to use what we call a code key.
That's right, a little code key or simply a device that puts the vehicle's computer into diagnostic mode. And to do that, we're going to insert this code key into the diagnostic connector. Now on this car, it's located under the dashboard here, just near the steering post, and it has a little plastic connector that I'll pull off that says diagnostic connector. Sometimes though, a car won't have the little plastic cover. It will have simply a open connector such as you see here, and it has a lot of terminals in there. The top two on the right are the ones we want, and I'm going to insert the code key into the top two terminals on the right, which starts the service engine soon light to flash. Now the computer turns this light on and off to tell us what the codes are. Right now it's flashing a code 12. 1, 1, 2. And it's been doing that. It flashes each code 3 times. There was 3 flashes. 1, 2, 3, 4. A 3 and a 4 is a 34.
Okay.
1, 2, 3. 1, 2, 3, 4.
And again, as we mentioned, it'll flash the code on a GM vehicle 3 times, so you can actually see it the second or third time in case you missed it the first time around.
And there was the third code 34, so we have a code 34 in the computer.
Okay.
A code 12, which is the test code, and a code 34. There's a very long pause here, Scott. I think the computer is done. It's checking itself out. If it's done, it'll flash the code 12 again, and it just did. It just started flashing the code 12, so it started all over again from the top.
Okay, so the next thing we're going to do is we're going to take that code 12 and code 34. Of course, code 12 we know is just the diagnostic mode for this vehicle, but the code 34, when we look it up in the manual, says it's a mass airflow sensor circuit problem. So we've got our starting point. The other thing that we want to do then is take our manual, turn it to the actual diagnostic chart. Now we can do one of two things at this point in time. We can either go out, test the mass airflow sensor, which will show, and if we don't do that, you can actually go down the trouble code 34 chart with your digital volt ohm meter until you find out what the actual problem is.
Now, after we've finished extracting the codes and determining their meaning, all we have to do is turn the ignition switch off, remove the code key, reinstall the plastic cover if your vehicle is equipped with one, and there you have a very simple test to determine where you need to be working on your vehicle.
Now we have to get the codes out of the vehicle once we're done with our service, and that's real easy to do also, Jim, isn't it?
That's right. To erase the codes once we're done, simply disconnect the battery cable for a few moments, or if you have a keyless entry system or a programmable AM/FM radio where you may not want to reprogram it, simply find the fuse in the fuse box that says ECM and remove that fuse. That too will clear the memory.
Okay, so as soon as you've got your service done, clear the memory, drive the vehicle, and then check for codes again.
Retrieving service codes from a General Motors vehicle is very easy. Just follow these simple steps. Locate the diagnostic connector. It will usually be found under the vehicle's dash. Insert the code key into the diagnostic connector and turn the ignition key to the run position. Observe and record the codes flashed by the check engine or service engine soon light. Next, reference a service manual or tech tip to determine the part or system indicated by the codes. Locate and follow the diagnostic chart in a service manual to troubleshoot the part or system. Now, turn the ignition off and remove the code key. After making your repairs, clear the codes from the computer's memory using one of the methods described.
Now, removing trouble codes from a Ford vehicle is a little bit different, but there are a couple things that are identical, and that is having your notepad to make sure you can write down the trouble codes so you can refer to them later on, and also make sure that you have the manual for the type of vehicle that you have so you can look the codes up and know where to begin your diagnosis. Now, Jim, the ALDL on Ford vehicles is not located under the dash, is it?
No, it sure isn't. It's in fact in the engine compartment, and really it could be located almost anywhere, Scott. Sometimes there is a small connector that's marked EEC test, and the diagnostic leads will be plugged into that connector, such as we have here. And I'm just going to reach down and remove those. Sometimes you need a small screwdriver to pry the connector loose.
Okay.
Other times simple thumb pressure will get the job done. And if you don't have the little cap that says EEC test, these connectors will just be hanging into the engine compartment. So look around until you find them. And these are the connectors that we use to put the vehicle into diagnostic mode and to get out the codes.
Okay.
Now we're going to need a tool called a code key for that. Now here's the code key, and I'll insert it into the connector and put the vehicle into diagnostic mode. One end of the key gets plugged right into here, and the small connector gets plugged into the other end of the key, just like that. Now we have just put the system into diagnostic mode.
But we don't have a light that's flashing codes yet, do we?
No, we sure don't. Now, some Fords, though, have a check engine light that will flash, like GM's and Chryslers. But most of the cars out there don't. So we'd like to show you how to get the codes out when you don't have a check engine light on the dashboard. And for that, you'll need a simple tool. This is a Ford EEC4 diagnostic connector. It has a little check engine light on it that will blink out the codes. And besides that, it has two electrical connections. A small one, the green side here, which we'll use to plug into the diagnostic connector, and this is where the codes will come out, and we plug it right into this terminal here.
Okay.
And the other end, which is a large alligator clip with red markings, goes to the battery plus terminal.
And I'll hook that up over here.
And now you can see that we've powered the system up, the light is on, and we're all ready to get codes from this car. All we need to do is to turn the ignition switch on to the run position, but not starting the car, and then the computer will turn all sorts of solenoids and things on and off, and then when that's done, we'll start to get codes.
Okay, let me go turn the key on, Jim. Okay, there it is. And we can hear some of the solenoids.
Yep, there goes the fan.
Kick the fan on and off.
Now we'll start to watch the light, and then we'll get our codes. 1, 2, 1, 2. A 22.
Okay, I'll write that down.
1, 2, 1, 2, another 22. So that code's been repeated twice. Now that's the end of our on-demand codes. In other words, what's wrong now?
Okay.
That light we just saw is a separator code. There's a long pause, a separator code, a long pause, 1, 2, 1, 2.
Okay, so it's giving us a 22 again, so that's the same code.
1, 2, 1, 2. 22 again. Now, after the long pause, what we got was memory codes. So that 22, not only is there something wrong right now, but it was also in the computer's memory.
Okay.
So now we know that we have a part that we can look up in the manual that apparently isn't working properly, and at least we'll know where to start our diagnosis of this vehicle.
Now code 22, Jim, says we got a mapper barosensor problem, and here it is on this vehicle, and what we've actually done is unplug the electrical connection to make our code 22. So before we go any farther with our engine run test, we've got to correct our earlier problem, don't we?
That's right, Scott, and in this case all we have to do is plug the sensor back in, and by doing that the map barosensor is back in the system, and when we start to resume our testing, the computer will think that we've repaired the problem.
Okay, now the same thing could happen if you had a bad or open circuit wire going to your mapper barosensor, or if the mapper barosensor was bad or defective. So you would have to correct that problem before you go on to the engine run test. In our case, it was an unplugged connector, so we've reconnected it, we're ready to go on.
Right. Now the next thing we'll do is the engine run test. We're going to run the engine and let the computer see if it can find anything else wrong.
Okay.
Now to do that, the engine has to be at full operating temperature, so you're going to have to run it for a few moments to get it up to temperature before you can do your tests. Now this engine is pretty warm still from when we pulled it in, but we probably should run it for a few moments anyway.
Okay. Why don't I go start her up?
All right. Runs a lot smoother now.
Yep, it sure does. Okay, and we only have to probably run her for 10-15 seconds here because, like we said, it was warm when we pulled it in.
Right. Now, after the engine runs a while, we do need to turn it back off.
Okay, I'll do that.
And we have to wait 10 seconds. This 10-second interval will allow the computer to reset itself between a cold start and a hot start. So after 10 seconds is up, Scott, go ahead and start it back.
Okay.
Now, I'm going to reconnect the code key, and when I do that, the computer will start a self-evaluation.
All right, now we're going to be watching our indicator light.
We're going to be looking for a dynamic response code. When it flashes once, we have to goose the throttle.
Okay. So actually during this run test, there are things that you have to perform. You can hear the idle changing as it's going through the different circuits and checking things out.
I suppose we ought to mention here that the computer's doing all of this. We're not doing any of this.
Right, good point.
There's our code.
All right.
1, 2, 3, 4, 5, 6, 7.
Okay.
1, 2, 3, 4, 5, 4. 74.
Okay, I'll get that written down.
1, 2, 3, 4, 5, 5. 1, 2, 2. 52.
Okay.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 74. Now they're repeating.
All right.
1, 2, 3, 4, 5. 1, 2, 52.
Okay.
So that's what we've got, a 74 and a 52. And the light hasn't come back on, so we know that we're done.
All right, I'll shut the engine off. Okay. Now, let's take a look to see what our codes were when the engine was running. Now, what we've got here, Jim, it looks like, is our code 52 first. It says it's a power steering pressure switch problem. If you've got a code 52 with the engine not running, you probably want to check into that circuit. What it does also mention here, with engine running test, it just means that we didn't take the steering wheel and turn it to lock during our test. So
That's
it's
right.
actually telling us what we didn't do and we should have done during our test. So
That's right. We should have turned the steering wheel all the way to the right and then all the way to the left
okay.
after the dynamic response code.
Right, okay. Now, our 74, let's see what that has to say. And our code 74 basically says we've got a brake switch problem. If we did have a code 74 when the engine wasn't running, we'd want to check out that brake switch. But engine running, it says we did not step on the brake pedal during our test. So what we would want to do at this time is actually rerun our test, and after that dynamic code came, we would snap the throttle, and then we'd want to actually step on the brake pedal once and turn the steering wheel all the way from lock to lock.
That's right. That's
Okay.
right.
And that's because this vehicle actually has a check engine light in it, and we could watch the codes right in there.
That's right.
Okay.
Well, this then would conclude the testing on our vehicle. The only thing that I would like to mention at this time is clearing the codes. And to clear any codes you might get on a Ford, all we have to do is unplug the code key from the connector as we're getting the codes, the engine running codes.
Okay.
And unplugging the key anytime after the codes start flashing will clear the memory, and then you're done.
Okay, sounds good.
Extracting Ford service codes is not a difficult task. These following steps explain how. Locate the EEC test connector, usually found under the hood. Insert the code key and test light is shown. Observe and record the codes flashed by the test light or dash light. Now, perform the engine running service code test. Watch for the dynamic engine response code, perform the required duties, and observe and record the service codes flashed. Once the codes have been given, reference the codes recorded in the service manual or tech tip. After the repairs are completed, clear the service codes by removing the code key during another engine running test.
We're sitting in a late model Chrysler vehicle. We're going to extract the trouble codes from the computer system. Actually, Chrysler vehicles are one of the easiest ones to do. But I still have my pad and paper and my manual along with me to tell me where to start diagnosis once we've got the codes out.
Now, like all vehicles, we must count the flashes of the check engine light or other diagnostic tool that we have attached to the system. In the case of the Chrysler, there is a check engine light, but we don't have a diagnostic connector to worry about or any special tools. All we need is the ignition key. We simply insert it into the ignition switch and turn the system on, off, on, and leave it on.
Okay, now we're going to observe the check engine light, and it's on right now. Bingo, went out, should start flashing codes.
1, 1, 2.
Okay.
That's a 12. 1, 1, 2, 3, 4. That's a 14.
Okay.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's a 55.
Okay.
And that's our last code. The lamp has stopped flashing.
Yep, as a matter of fact, if we look in the manual, the 55 says end of message for trouble codes. So that's nothing that we have to work on. That just means our system is done telling us codes.
Right.
But our 12 and 14 are telling us we've got a problem to look into.
That is correct.
All right, if I look in the manual here, a 12 says we've got a problem in the memory feed circuit, okay? So basically that's telling us we probably got a wiring problem.
Yeah, usually that just means we have an open circuit somewhere, and that'll be easy to check later.
Okay, and we've also got a code 14 which says a map sensor electrical problem. Okay, so those two are probably going hand in hand. There's a good chance that either somebody left the map sensor disconnected when they were working on the vehicle, or possibly that the wires have gotten burnt or frayed or something like that's happened to create an open circuit.
That's right.
Now once we've got that repaired, we have to remove the codes from the computer, don't we, Jim?
Right. Now the Chrysler, like all the other vehicles, have a fairly simple method for removing the codes. Actually, you can either disconnect one of the battery cables for a few moments, and that will erase all of the computer's memory. That will also erase the memory of your radio if you have some programs in there. So if you don't want to erase your radio's programming, only the computer's memory, find the fuse for the computer in the fuse panel and just pull that out for a few moments. That'll take care of the computer's memory while not interfering with what you've got in your radio.
Sounds great.
Obtaining the service codes from a Chrysler vehicle is a snap, as you've already seen. Begin by inserting the ignition key. Then, activate the self-diagnostic system by cycling the ignition key as shown. Now, observe and record the flashes of the check engine light. Reference the service codes in a service manual or tech tip. Locate and follow the diagnostic chart in a service manual. After the repairs are completed, remove the service codes from the computer's memory.
Our drivability problem this time is on a Chrysler vehicle, Jim. And what we've got is we've got the kind of that rotten egg smell or odor coming out of the tailpipe, the poor fuel economy, and the driver just complained about the throttle response just isn't what it used to be. Now I use the key method to pull the codes on the car. On, off, on, off, on. I came up with a code 22. And when I looked in our book, a code 22 said O2 system full rich or full lean. So boy, we know where to start, don't we?
We sure do. It's in the oxygen sensor circuit, but we don't really know where. Could be a wire, a computer problem, could even be the oxygen sensor itself. So best thing to do is remove it from the vehicle and take a look at it and see what color it is. Maybe that'll help us determine the problem.
Sure, there's three things that you can do to an oxygen sensor. First thing is you can perform a visual inspection.
Right.
Second thing is you can do an on-the-bench test. And the third thing is you can test it on the vehicle, and we'll do all three of those right now.
Well, let's take a look at the colors first. Here's one we took from a vehicle that has sort of a grayish color. You can see a little bit of a coating on it, but that's normal, Scott. That shows just, it's been in there for a long time doing its job, and it has normal combustion type color.
Okay.
Now here's another one that is normal also. It doesn't have quite the amount of deposits on. It's got a slightly reddish tint to it, and that reddish color comes from the gasoline additives that we have nowadays. So that's a pretty good looking oxygen sensor too. It's just been in there a long time doing its job, and we had to replace it just as normal maintenance.
Okay.
But here's one that's all black. See that rich black color? And that comes from an over-rich mixture. And it has coated the whole thing with carbon.
Yep.
So maybe this is part of the problem that we're having on the vehicle that you just described.
Okay, now we've got some lighter colored ones over here too.
Yeah, now this one here is just a slight hint of gray, and it looks like someone's been running leaded gas in this car.
Okay, and that'll contaminate the sensor, and that could create our problem that we're having right now. The sensor is not as active as it used to be because it is now contaminated by leaded fuel.
Right. And the last one here that we can look at is one that's kind of a chalky white color. And this usually shows contamination from using antifreeze that's leaking through the head gasket someplace, or anywhere where it gets into the cylinders.
Sure.
Sometimes using a silicone-based sealing compound that is not the right type will also cause this type of contamination. So silicone or antifreeze will turn them white.
Okay. Now how about our bench test? We finished our inspection and determined that, let's check this one right here. This one came out of the vehicle and you said it looked fairly well.
Yeah, it really did. Now, doing it on the bench simply requires the use of a propane torch and also a voltmeter, a digital voltometer.
Okay.
Now, the whole idea here will be to put the tip of the oxygen sensor into the flame where there is no oxygen. Now, on the car, an oxygen sensor that's detecting a lean mixture will produce a low voltage, and one that's detecting a rich mixture will produce a high voltage. Now there's no oxygen in the flame, so that's kind of like a rich mixture.
Okay.
So as we stick it in the flame, the voltage should come up. And as I pull it out of the flame, the voltage should go down. And that's our test. But there's a time limit on this. When I put it in the flame, the oxygen sensor must be able to produce 9/10 of a volt within 1 minute. And when I pull it out of the flame, the voltage must drop within 3 seconds to where it was before. It's a very, very simple test, and we can do that together right now.
All right, and the other thing we're doing is we're actually heating the oxygen sensor tip to 600 degrees Fahrenheit, which has to be done for a bench test or an on-the-car test, either way. Before we light the torch, I'm just going to put my safety glasses on, and we'll get this lit, and I'll point this away from us. Okay, we have that lit now.
I'm turning the voltmeter on to the lowest voltage scale, the 2-volt scale, because these oxygen sensors only produce about 1 volt or so.
Sure.
So you need to be on your low scale. Then we're going to connect the red lead of the voltmeter to the wire end, in this case, or the terminal that you would have. And you must remember to use the black wire. Sometimes an oxygen sensor has more than 1 wire. Some have little heaters in. So always remember to use the solid black wire.
Good point.
And then connect your ground lead of the voltmeter to the shell of the oxygen sensor. You can just hold it like this.
Okay.
Now I'll insert it in the flame, and we'll see if this oxygen sensor can produce 9/10 of a volt within 1 minute.
Okay. Well, it's already starting to produce a voltage. 5, 6, 7, 8, 9/10 of a volt already.
Okay, so far
1
so
volt.
good.
Yep.
Well, I'm going to pull it out of the flame, and we'll see if it drops.
1001, 1002, 1003. And it's right back down to 0.008 and dropping.
Okay, great. So I think that this one here, although it still functions, has just been in there quite a long time and was replaced just because of maintenance. So this is a good oxygen sensor, and that's how you can tell if they're good or bad right on the bench.
Okay.
Now one thing I'll do though is put this down into an ashtray or someplace where it can cool off, because they're quite hot for a while.
All right. Now there's an on-the-vehicle test that can be performed also. Why don't we head out in the garage and show them that one?
Okay.
Now, along with a simple bench test, you can also test your O2 sensor right on the vehicle, and we're going to demonstrate that right now, right, Jim?
That's right. Now, basically what we're going to need, Scott, is a voltmeter set on the 2-volt scale because the O2 sensor produces a very small voltage. And I'm going to connect the voltmeter first to a good ground. The negative lead gets connected to a good engine ground.
Sure.
And then I'm going to reach over and unplug the O2 sensor lead and connect the positive lead of the voltmeter to the O2 sensor's lead. Now we'll be able to measure the voltage while it's right in the engine. Now we're going to have to run the vehicle and change the air-fuel mixture ratio. The simple way to do that would just be to create a vacuum leak.
Sure.
And there's a vacuum port right here on the top of this engine with a little rubber cap on. So if you have one of these on your car, there's a little clip that you can use a pair of pliers to remove and get that out of the way, and then simply pull the little boot off. And that will create the vacuum leak that you need to change the mixture. So I'll start the car, and we'll do that.
All right. Now, we've previously run this engine for a little bit of time to warm it up, too. Okay. You might need to run the engine for a little additional time, and our meter's starting to come up now. So I think our O2 sensor is warm enough, and it does have to be at least 600 degrees Fahrenheit for this test to work.
Now I'm going to go ahead and open up the vacuum port, and we should watch the numbers drop as we lean the mixture.
Yep, going way down. Put your finger over it, plug the vacuum leak, numbers go back up. Way down, and back up.
Now, as you can see, the engine almost stalled on this test, and on some vehicles it actually would stall. So on those vehicles, we'll have to do something called a propane enrichment test.
Sure.
And so I'm going to take this valve, which we have screwed to a propane bottle. It's a regular propane bottle with a special valve on it for doing this test, and connect it to the vacuum port.
Okay, Okay, now we have a slight vacuum leak introduced, so we're seeing a real low voltage on the voltmeter, which is a signal of a lean mixture. Now if we open the propane bottle up, our reading should go up. There it goes, way up.
And as I shut it off, it goes back down.
Way back down.
But this gives us the opportunity then to test an O2 sensor on the vehicle with either a vacuum leak or a propane enrichment test.
Let's review the test procedure for an oxygen sensor that has been removed from the vehicle. The first step is to remove and inspect the oxygen sensor. Set the digital voltmeter, or DVOM, to the 2-volt scale. Connect the DVOM red lead to the black wire of the O2 sensor and the black DVOM lead to the oxygen sensor outer shell. Heat the sensor tip in a torch flame. The voltage should exceed 0.9 volts in less than 1 minute. Remove the sensor tip from the flame. The meter reading should reach 0.1 volts or below within 3 seconds. Now let's review the test procedure for an oxygen sensor that's still installed on the vehicle. Connect the voltmeter leads to the oxygen sensor lead and a good ground. Locate a manifold vacuum port or source. Start and run the engine until the meter readings start to vary or toggle. Create a vacuum leak at the port or source located earlier. Observe the meter reading. The voltage reading should fall below 0.1 volts with a vacuum leak and rise above 0.5 volts when the vacuum leak is plugged.
The tools you will need to replace your oxygen sensor include a 3/8 drive socket set, a special oxygen sensor socket, and a torque wrench. In some cases, you may also need a soldering gun and solder, a wire crimping tool, and some heat shrinkable tubing and a cigarette lighter or source of heat. And in all instances, you'll need the correct new oxygen sensor for your vehicle.
The first step in replacing your oxygen sensor is to start with a cool engine. Then locate the sensor and clip off the existing wire or wires near the sensor itself. With a socket of the correct size, remove the old sensor from the exhaust manifold. For ease of removal, you may want to use a special oxygen sensor removal socket as shown. Place a small dab of non-volatile anti-seize compound on the threads of the new oxygen sensor. Install the new sensor in the threads, starting it by hand, and tighten to recommended specifications.
Now let's review the steps involved in replacing an oxygen sensor. First, cut the lead wire from the old oxygen sensor. Then remove the sensor from the manifold or pipe. Next, apply anti-seize compound to the threads of the new sensor. Install the new sensor and torque to the correct specification. Lastly, reconnect the electrical lead.
Okay, now if you've got a vehicle that's running too rich, you might have some black smoke out of the tailpipe, and on this vehicle it's getting pretty poor mileage, Jim. When I went in and pulled the trouble codes out of the computer, I got a code 15. When I went to my trouble code chart, it simply says right here, code 15, open coolant sensor circuit. Now you've got a quick test of that coolant temp sensor, don't you?
Sure do. It's another one of the 2-minute tests that you can perform at home to find out if your coolant temperature sensor is working.
Okay.
Now here's one, just like the one that's in this vehicle here. And of course it's out of the vehicle, it's not warm, it's cool. Inside of a coolant temperature sensor is a thermistor, which is a device that changes its resistance with temperature.
Sure.
Now in this particular case, as I said, it's cool, so it's going to have a specific reading on the ohm meter. I'll take our meter and put it to about the 20,000 ohm scale, or the 20K scale,
okay,
and connect one lead to the body and the other one to the terminal, and we'll get a specific reading. In this case, about 1,930 or so ohms.
Sure.
Now remember, this is a cool one. This engine is quite warm. It's been running. So to illustrate the difference between a cool one and a warm one, we simply take and connect the black lead to a good ground, the positive lead to the sensor terminal, And here we can see we're at about 460 or 470 ohms. Quite a difference.
Yeah, there certainly is. Now, when you actually perform this test on your vehicle, you're going to be running the engine. You connect your meter up. You're going to run the engine for 2 minutes, and you're going to look for a 200 ohm difference within that 2-minute period. For sake of illustration, we did it this way. Now, if you don't find any change, boom, that's your problem. Replace the coolant temp sensor, and you're on the road again. If you do find a change, your coolant temp sensor is okay, and then you've got to get back in the book and do a little bit of work and go to your actual trouble code chart and follow your diagnostic chart out to find the problem. In this case, you'd probably find an open coolant sensor circuit wire or something in the ECM.
To test a coolant temperature sensor on the vehicle, do the following. Attach the red lead of the digital volt ohm meter to the coolant temperature sensor terminal. Attach the black lead to a good engine ground. Observe and record the meter readings with the engine at ambient temperature. Start and run the engine for 2 minutes. Observe and compare the meter reading to the first reading. Look for a minimum 200 ohm difference, indicating a good sensor. If the sensor tests okay, locate and follow the diagnostic chart in the proper service manual.
To replace your engine coolant temperature sensor, the tools you will need include a standard or metric wrench set, a hex wrench set, a regular blade screwdriver, liquid pipe thread sealant, a gallon of antifreeze, a large drain pan, and the correct coolant temperature sensor for your vehicle. Whenever working on your vehicle, always start repairs after the engine has cooled down. This will prevent personal injury due to hot engine coolant. The first step whenever working on the electrical system is to turn off all the accessories, including the ignition key. Then, disconnect the negative battery cable. This will keep spike voltages from damaging other components and will prevent the electric cooling fan from engaging during repairs. Before disconnecting the negative battery cable, be sure to write down any pre-programmed electronic radio stations on a piece of paper. This will allow quicker reprogramming when repairs are completed. On most vehicles, the engine coolant temperature sensor will be located either in the coolant passages of the intake manifold or near the thermostat housing. Next, open the radiator drain and lower the level of the fluid in the system. This will prevent coolant from spilling out onto the engine after the sensor has been removed. Make sure you have a drain pan to catch the old coolant. Then remove the radiator cap. On many late model vehicles, a bleeder plug must also be removed from the thermostat housing. Release the locking tab on the electrical connector and remove the electrical connector from the engine coolant temp sensor. Using a wrench or the appropriate socket, remove the old sensor. Compare the old sensor to the new one to be sure of correct replacement. Inspect the old coolant temperature sensor tip for scaling and deposits. If scaling is evident, we strongly recommend the cooling system be flushed and the engine coolant also be replaced to prevent scaling and deposits from forming on the new sensor. If the new temperature coolant sensor's threads are coated with a pipe sealant to prevent coolant leakage, no additional sealer is necessary. Install the new sensor and tighten it securely. Before reconnecting the electrical connector, inspect the connector for signs of damage and for wetness. If the connector is wet from engine coolant, inspect the entire wire for corrosion and replace as necessary. Reconnect the electrical connector to the new sensor, making sure the locking tab is secure. Add a new coolant mixture of 50% water, 50% antifreeze to the radiator until it reaches the radiator cap seat. We recommend you do not reuse the old engine coolant that was removed. On vehicles where a threaded bleeder plug was removed, add coolant into the radiator until it reaches the bottom of the bleeder plug hole. With sealer on the threads, reinstall the bleeder plug in the hole and tighten it securely. After installing the bleeder plug, continue to fill the radiator until it reaches the radiator cap seat. Reinstall the radiator cap. On vehicles with a coolant reservoir, Fill with new engine coolant until the level is between the minimum and maximum marks. Reconnect the negative battery cable. Start the engine and run until normal operating temperature is reached. With the engine idling, add coolant to the reservoir as needed. And lastly, reprogram the electronic radio stations if so equipped.
To replace your coolant temperature sensor, follow these steps. Turn off all accessories on the vehicle, then turn the ignition key to the off position. Locate the coolant temperature sensor found in the engine block. Drain the engine coolant from the radiator. Disconnect the coolant sensor electrical lead. Remove the coolant temperature sensor from the vehicle. Once removed, inspect the sensor tip for scaling or deposits. If any are found, flush and refill the cooling system. Compare the old and new sensors to ensure a proper fit. Install the new sensor using a liquid pipe thread sealant on the threads. Install the electrical connector and reconnect to the new sensor. Refill the cooling system with a new 50-50 mixture of water and antifreeze.
Okay, Jim, for sake of example, what I've got again is a late model GM vehicle. I got a sudden drop in fuel economy, sluggish performance. So what I went and did is I pulled the codes out of the ECM. What I found was a code 33. Well, I referred to the manual on that vehicle. Code 33 told me I've got a map sensor circuit problem. Where do we go from there?
Well, that really doesn't surprise me because a map sensor can cause a drastic decrease in mileage and some sluggish performance. But I think what we'll have to do is test this. I would suggest a quick 2-minute test to verify that code before we go any further.
Okay.
Now what we're going to need is a vacuum pump to supply the vacuum that the intake manifold would normally supply. We're going to need a voltmeter. And we're going to need some way to make it run. So I brought along a special tester for that. This is our universal tester again with the correct end on it for plugging into map sensors for this type of testing.
Okay.
So I'll get that plugged in, and perhaps you'd like to do the vacuum gauge while I get the voltmeter turned on.
What your map sensor does is it signals the computer as to how much load is on the engine, and therefore the computer adjusts the fuel mixture and the ignition timing to match that load.
Now what we want to do is watch the voltmeter here. As you apply vacuum, the voltage should change. And I suggest going to about 15 or 16 inches of vacuum and holding when you get there.
Okay, this is similar to our throttle position sensor test. You want to watch to see if the voltage changes evenly, and in our case it does, and I'm at 15 inches of vacuum, and it holds vacuum.
Right. After you've satisfied that the part doesn't leak at all, go ahead and release the vacuum, and the voltage should go back down to somewhere near where it was before.
And it does. Now this happens to be a map sensor off from a GM vehicle, and it's operating fine, so that is not our problem.
That's right. And since it's not our problem, on the vehicle you spoke about, we would have to go to our book that talks about diagnostic trees and trouble codes and find the map sensor diagnostic tree and just follow the step-by-step procedures for that map sensor. And what you'll find is that you either have a bad vacuum hose or an electrical connection, it could be an ECM again, but somewhere in there is where your problem lies.
Okay, so we know replacing the component at that point in time isn't going to fix our problem.
Right, although one day we found this one on a car that was bad, and let's show the folks how we found a bad one.
Okay.
Once again, we attach our lead. This one is from a Chrysler, by the way. And GM and Chrysler map sensors work the same way.
All right, I'll plug the vacuum hose from the hand vacuum pump in there. Now again, these tests can be done on the vehicle or can be done with the item off the vehicle like we're doing here.
Okay, once again the voltmeter is set on the proper voltage range, and you go ahead and apply the vacuum.
Okay, I'm applying vacuum. Nothing's happening. Nothing at all is happening. I'm at 15 inches. Now the vacuum gauge is staying steady, so the actual vacuum diaphragm in here is okay, but we've got an electrical problem with the map sensor.
That's right, Scott. The electronics in this device is not working, and that's why we don't get a voltage response. So this one is bad.
Okay, that would certainly create our problem. Now, What about Ford vehicles? They got something a little different, don't
They
they?
certainly do. This is the Ford map sensor, and although it's similar to the Chrysler and the GM in many ways, it's shaped a little bit differently. It has a 3-terminal connection and a vacuum port, but unlike the others, this does not change a voltage. This actually creates a frequency, and we have to read that on a frequency meter or even our tachometer. That'll work real well too. Why don't we go out to the car? There's one on the car. We can just test one on the car to show how it's done that way.
All right.
We'll need our
And vacuum pump?
right. We'll need our tachometer, and we'll also need our special tool with the correct attachment for the Ford, and I've got that right here. So let's take everything on out to the car.
Okay. Okay, Jim, here's our Ford vehicle. Set the vacuum pump here, and our map sensor sitting right back here up top, isn't it?
Sure is. Very easy to get at on this particular vehicle. Now, to test this, what we're going to have to do is first disconnect the vacuum line so that we can attach the vacuum pump, and the electrical connector so that we can attach the tester. Now,
Okay.
on this particular unit here, there is a little locking tab that you just push down with your thumb, and that aids in pulling off the connector. Now, here we have our universal tester, and I'll plug the Ford map sensor lead to it. Now, we don't use the light at all on this. All we're using this is for a power supply and a place where we can take the generated RPM and pick it up with the tachometer.
Okay.
Now, let me explain that. First, we'll simply plug into the map sensor, and then the map sensor is actually working now because we have our own power supply.
Sure.
It's producing a frequency based on what the map sensor is putting out right now. And for us to read that, all we have to do is take our meter and turn it to the 4-cylinder tachometer scale,
Okay.
attach the positive and negative leads, and there we have our frequency.
Sure.
Now, to change that, as the engine does, we'll attach our vacuum pump so that
Okay.
you can apply vacuum to cause the reading to change, and that way we'll be able to see if this map sensor responds to vacuum.
Okay, we're at about 491 just for reference point, and I'll start pumping it up. We'll see if it changes. And it is changing nice and slowly as I pump the hand vacuum pump up slowly. So what we're looking at is the electronics in it is working, and also the vacuum diaphragm is working. I'll stop pumping. We'll just make sure that diaphragm holds.
Right, watch the gauge for a few moments and make sure it doesn't leak down.
I can just release the pressure. We should be back about to our original reading, 490, and we are.
Right, so now we know we've got a good map sensor on this vehicle.
Testing your manifold absolute pressure sensor is easy. Let's look at the procedure involved in testing this sensor. First, connect the universal tester to the manifold absolute pressure sensor. Connect the vacuum pump to the vacuum port located on the sensor. Connect a digital multimeter to the sensor's electrical connection. Set the meter to the appropriate scale for your vehicle. Next, observe the reading shown on the meter. Apply vacuum to the sensor and note the meter reading. Typically, 5 inches of vacuum equals approximately 1 volt of change on the meter. Release the vacuum and observe the meter reading. It should be equal to the initial reading obtained earlier. If the sensor tests okay, refer to the proper service manual and follow the diagnostic chart for further testing.
To replace your manifold absolute pressure sensor, the tools you will need include a 1/4-inch drive socket set, a small regular blade screwdriver, a needle nose pliers, and the correct map sensor for your vehicle. The first step whenever working on the electrical system is to turn off all the electrical accessories, including the ignition key. Map sensors and vacuum sensors, depending on the type of vehicle, may be mounted in one of 3 positions under the hood. Normally, they will be located on the inner fender, on the vehicle's firewall, or they might be located on the air cleaner housing. Let's look at the removal and replacement of the map sensor located on the firewall. This procedure will be the same for map sensors located on the fender. First, remove the vacuum hose attached to the sensor. Release the locking tab from the electrical connector and remove the connector from the sensor. Loosen any mounting bolts and remove the sensor from the vehicle. Compare the old map sensor to the new one to be sure it is the correct replacement. Using the mounting bolts removed earlier, reinstall the new map sensor on the vehicle. Before attaching the vacuum hose, inspect it for cracks or blockage. If either are found, replace the vacuum hose at this time. Reconnect the vacuum hose to the new map sensor. Before attaching the electrical connector, inspect it for signs of corrosion and loose or broken wires. Clean corrosion and repair any damaged wires found at this time. Reconnect the electrical connector onto the new map sensor, making sure the locking tab is secure. Reconnect the negative battery cable, and you're done. Another style of replacement is one that is located on the air cleaner housing. Let's take a look at the removal and replacement of this type. First, remove the vacuum hose from the sensor. Release the locking tab from the electrical connector and remove the connector from the sensor. Using a small regular blade screwdriver, push the 4 tabs holding the bracket. Release the sensor and remove it from the bracket. Compare the old map sensor to the new one to be sure it is the correct replacement. Install the new sensor onto the bracket, making sure all the tabs are properly locked and the new sensor is secured tightly to the bracket. Once again, before attaching the vacuum hose, inspect it for cracks and blockage. If found, replace the hose. Reconnect the vacuum hose to the new map sensor. Before attaching the electrical connector, inspect it for corrosion and loose or broken wires. Clean any corrosion and repair any damaged wires. Reconnect the electrical connector on the new sensor, making sure the locking tab is secure, and you're done.
To replace your manifold absolute pressure or map sensor, follow these procedures. Turn off all electrical accessories and turn the ignition key to the off position. Locate the manifold absolute pressure sensor on the vehicle. Disconnect the vacuum line from the sensor. Disconnect the electrical connector from the sensor. Loosen any mounting bolt and remove the sensor. Install the new sensor. Inspect the vacuum hose for cracks or restrictions. Replace the hose if any signs of deterioration are found. Reconnect the vacuum hose to the new sensor. Inspect the electrical connector and clean or replace if corroded or damaged. Reconnect the connector to the new sensor.
Okay, Jim, I've got a new one for you. We're going to pick on our same late model GM vehicle, and this time I've got black smoke coming out of the tailpipe, sluggish engine performance, and guess what? I didn't pass the emissions test.
Do you have any codes?
Well, I pulled the codes, and guess what I came up with? Code 23. When I looked in the manual, code 23 told me I've got a problem in the MAT sensor circuit. MAT stands for manifold air temperature, or it might be called ACT on your vehicle, which is air charge temperature. In either case, that's what it told me to check out.
Well, I'm not real surprised. This temperature sensor measures the temperature of the air, so the computer knows how dense the air is, and then it knows how much fuel to add to it. So if this isn't working, you would have a rich mixture. You would fail your smog test.
Okay.
This one screws into the air cleaner or the intake manifold. Now, this type here usually just clips into a hole in the air cleaner. Whichever type you have, though, they're quite easy to test.
All right, we've got a 2-minute test, and what we're going to use is our digital voltometer again.
Why don't you go ahead and put that on the, about the 20K scale, while I connect the 2 leads of the ohm meter to the 2 leads inside the sensor.
Okay, we'll get a reading going here. There we are. Okay, we've got our reading.
Now the idea is to change the temperature of this sensor and then read the change on the meter.
Okay.
Your body temperature will do that, so as I touch that with my finger, the reading should start to change.
Yep, it's going down.
And then as I release it,
okay, we're going to watch to see it slowly come back up. Now the change going back up is obviously going to be slower than on its way down, but it did start changing going back up.
Great.
So we know this one is okay.
It sure is. Now there's another place that you can find this type of a temperature sensor, and that'll be inside of the mass airflow sensor. Now some vehicles have this kind of a device to measure how much air goes into the engine, and inside of it is a temperature sensor, just like the one we just tested. It's kind of hard to get at it with the leads of your ohm meter because we have a connection here with very small pins in it.
Okay.
This is my device that I use to test this whole mass airflow sensor, but if I plug that in, there are two terminals on here that will allow me to connect my ohm meter just to the air temperature sensor part of it.
Okay.
So as I connect from here to here, once again, you should have a reading on the meter.
And we certainly do.
And as I put my finger on the temperature sensor, we got to get some sort of a reaction.
Yep, that's dropping down very rapidly.
Okay, same test as before. And then as I let it go, you may begin to see a change.
Yep, it's just starting to slowly go back up. Obviously, your temperature, again, going back up is going to be much slower than it actually going down. Now, if you find that your air charge temperature sensor is okay and you still have that code 23, what you're going to want to do is refer to your emissions and diagnostics manual, find the chart for your code 23, and what you're again going to probably end up finding is either a wiring problem or a problem in a connector or the actual ECM itself.
In either case, a 2-minute test will find it pretty quick.
Let's look at how easy it is to test an air charge temperature sensor. Set the digital volt ohm meter to the 20K scale and connect the 2 meter leads to the terminals of the sensor. Touch the tip of the sensor or breathe on it and note the changes on the meter. If no change is noted, the sensor must be replaced. If the sensor passes this test, locate and follow the proper diagnostic chart to pinpoint the fault.
To replace your air charge temperature sensor, the tools you will need include a standard or metric wrench set, a regular blade screwdriver, liquid pipe thread sealant, and the correct air charge temperature sensor for your vehicle. To prevent burns and make the job easier, always begin with a cool engine. The first step whenever working on the electrical system is to turn off all the accessories, including the ignition key. Then locate the air charge temperature sensor. On many vehicles, it will be located either in the intake manifold or in the air cleaner housing or air duct itself. In either location, it may be necessary to remove the air duct or air cleaner assembly in order to access the sensor. Once the air charge temperature sensor has been located, release the locking tab on the electrical connector and remove it from the sensor. Remove the old air charge temperature sensor from the vehicle. Compare the old sensor to the new one to be sure of correct replacement. Coat the new sensor's threads with a liquid pipe sealant to prevent air leaks. Install the new air charge temperature sensor and tighten it securely. Before reconnecting the electrical connector, inspect it for signs of corrosion or damage. Clean any corrosion and repair any damage found at this time. Reconnect the electrical connector to the new sensor and reinstall any components earlier removed. You're done.
To replace your air charge temperature sensor, do the following. Turn off all accessories, including the ignition switch. Locate the air charge temperature sensor on the engine. Disconnect the electrical connection from the sensor. Remove the old sensor from the vehicle. Compare the old and new sensors to ensure correct replacement. Apply a liquid thread sealant as needed and install the new sensor. Be careful not to over-tighten the new sensor if it is located in an aluminum intake manifold. Inspect, clean, and reconnect the electrical connector to the new sensor.
Well, Jim, we still got that same GM vehicle, late model, and now I've got a problem with it at idle. At idle, it seems to want to die on me once in a while, and also I've got that same periodic check engine light that's came back. What do you think?
Well, since you have a check engine light, you're going to have to pull the codes.
Which I've done, and when I did pull the codes, I came up with a code 34. When I went to the manual, code 34 told me MAF sensor. MAF stands for mass airflow sensor, and they're located in a readily accessible spot underneath the hood, right in the air cleaner housing. How's our 2-minute test?
Well, we do have a 2-minute test for the mass airflow sensor, and if you'd like to take and hold this and help me show everyone how it's connected up. This is our universal tester. Now, the first thing you'll notice is we don't have the 9-volt battery on here.
Okay.
I have it connected to a transformer which will supply us with 12 volts for our testing purposes. We could have hooked it to a car battery with the car battery jumper, but this was a little bit handier for our purposes today. The point to remember is that mass airflow sensors are not 9-volt devices, they're 12-volt devices, so don't use your 9-volt battery to try to run these things. That won't work.
Okay, how about our connections?
Well, the connections are, there's 3 terminals. The one over here on the left is positive, so that's where I've got the red one connected.
Okay.
The one way over on the right is negative, so that's ground. That's where the black one goes. And the center terminal is where the pulses come out of. So to that terminal, I have connected the clip for the LED and the clip for this meter, which we're going to put on the RPM scale.
Okay, 4-cylinder scale.
Right, the 4-cylinder scale. We need the tachometer to measure this because these produce a frequency. And the frequency can be measured with a tachometer for our purposes, and the 4-cylinder scale is the most accurate scale for this. Now, I'll hold this and call your attention to the lamp. It should be flickering right now.
It is.
Now that flickering lamp shows us that this is producing a frequency or pulses, and at the same time we should be able to read them on the meter.
Yep, and we can.
Now to test this, all I have to do is blow through it because this measures airflow. And of course when I blow through it I will increase the airflow, which should cause the lamp rate to increase, and you should get a different reading on the meter.
Okay.
So let's do it a couple of times. Let's watch the meter first as I blow through here.
All right. Way up. 165 counts, and now she's going back down to where it was originally.
Okay, let's watch the lamp.
Yep, the lamp speeds up so much that it actually almost looks like a dim lamp. Now it's back to its flickering.
Right, that high speed. In fact, it almost looks like it's on all the time, doesn't it? Because the frequency is so high and the lamp rate is so high. Now, at this point in time, you might think that this is a good part. But one of the things that mass airflow sensors have a habit of doing is coming apart inside, especially in the electronics portion of it.
Sure.
So if you'll take an object such as a screwdriver and tap on that, we should be able to see a change in the output if it's loose, if it's defective. Now you can't do that with the lamp, you must do that with the meter.
Okay.
So observe the meter while I give it a tap.
Ooh, way up. Way down and way up.
So it's going to be varying all the time. The reason why this was running when we started the segment was to get it good and warm. If you suspect an intermittent problem with your mass airflow sensor, hook up your tools like we've done here and set it on the counter or just leave it on the car for 10 or 15 minutes. Get it good and warm and then make your test, and you'll find a bad one, if it is bad, just as you and I have done now.
Okay, and this could cause our problem with the engine stalling at idle as well as our intermittent check engine light.
That's right.
Now there's 2 styles of these, correct?
It sure is. This one is a 3-terminal, and as soon as I get everything disconnected, perhaps we can show that there are actually 3 terminals in here, and that's where we had the tools connected a few moments ago.
Okay.
Now the one I'm bringing up alongside is a 5-terminal, and you can see we've got a different type of connector on there, so we can get into all 5 terminals.
Okay.
So what we'll do then is connect our universal tester into the lead, and that will power the mass airflow sensor, and then hook up the tachometer to the output, and we should be getting a reading.
We are getting a reading.
And the light should be flickering.
And our light is flickering.
Okay, now all I have to do is again blow through the device, and we'll see if it works. We'll check the gauge first, I guess.
All right. Gauge goes way up.
Okay,
196
great.
counts, back down.
And now how about the light?
Yep, same thing with the light. Now the light is actually going to almost a full steady beam, so that's showing us our frequency change.
Right. And then of course if we were to tap on the thing, it should be fairly steady instead of jumping all over the place like it did the last time.
Yep, no change at all.
Okay, great. So now we know we've got a good one. Now, since this is a good one, though, it's not the type of problem that you're having. So if you test your mass airflow sensor and find it to pass the test, you're going to have to go into your diagnostic troubleshooting chart and follow the directions here to arrive at either a bad wiring harness or an electrical connection, maybe even a bad computer.
Okay, but we can do these same tests right on the vehicles. We've got one sitting over there. We'll disconnect our equipment. We'll meet you right over at the car. Okay, now we're over at the vehicle, and Jim, why don't we explain to them how we've hooked the meter and our tester up?
Well, this particular mass airflow sensor is a 3-terminal sensor, so we're going to have to use our universal lead again. It's even marked. We don't have to look this one up in the book. It says A, B, and C, plus, minus, and A, it will be frequency. Now, all we have to do is connect the red lead of our tester to C, because it says plus, that's power.
Sure.
We connect the black lead of the tester to B, because it's got the negative mark there, that's ground. And on the A terminal, where the pulses will come out of, we'll connect our tachometer lead, the red one. And now the other end of the tachometer, the black one, we must ground somewhere. So you could use an engine ground. I like to use the back terminal on the universal tester, because that is the negative terminal when it's connected to a battery. And by the way, the battery we have it connected to is the car's battery. We're using the 12-volt adapter here because this is a 12-volt device.
Sure.
Now, the green lead will be connected to the tach lead because we want to measure those pulses, and it also powers the whole tester up. See, our light just came on when I made that connection.
Sure.
Now let me just mention this white lead. This is a positive or a hot lead, and I've got it clipped out of the way here so it doesn't bounce on the engine somewhere and perhaps arc can cause a problem. So just get that one clipped out of the way.
Good idea. Then we'll take our tachometer and we'll put that on the 4-cylinder scale. And as you can see, we're not getting any reading with the vehicle. The engine not running, no air going through it. And our light, if you can hold that over here a little bit, Jim, our light is just steady right now. So
that's right. That's very common on really late model mass airflow sensors because they don't produce any reading at all until air is actually blowing across it. So if I go start the engine now, we should be able to get that type of a reading.
Okay, let's try it. Okay, well, we're not actually getting much of a reading here, so I'm just going to flip her down to another scale. And sure. Okay, I just took it down to the 8-cylinder scale. So if you don't get a reading on your vehicle when it's on the 4-cylinder scale, just flip it down to another scale until you do get your reading.
Right, that'll be common with late model vehicles also. So just use your tachometer, get it onto a scale that gives you some sort of an indication. Now, I'll rev up the engine a little bit and we'll see if we get any kind of a response. Now you can see that we do have a response, and we know that the sensor is producing a frequency. Now to test it, to find out if we have any loose connections inside, in the electronics portion, we'll use the screwdriver again to tap test.
Okay, and our reading stays pretty constant.
I'll go turn it off.
Now, the other thing that you want to look for when you're performing a tap test is when you have the engine running, you tap that mass airflow sensor and you listen for any RPM change in the engine. If you've got a sudden drop in RPM or a little blip in RPMs, that's telling you you've got a bad mass airflow.
Let's review how to test a mass airflow sensor that has been removed from the vehicle. Connect the mass airflow sensor tester to a 12-volt power supply. Connect the universal tester leads and the digital volt-ohm-meter leads to the sensor. Turn the meter on and set the scale to 4-cylinder tach or RPM. Observe and record the meter readings. Blow through the sensor and observe the difference in the meter reading. Next, tap on the sensor and observe any meter reading changes. If the mass airflow sensor passes these tests, locate and follow a diagnostic chart to pinpoint your specific problem. Now let's review the testing of a mass airflow sensor while it is still installed on the vehicle. Connect the digital volt-ohm-meter leads and the universal tester leads to the mass airflow sensor. Connect the universal tester power lead to a 12-volt power source. Observe and record the initial meter reading. Start the engine. Observe and compare the meter reading to the initial reading. Increase the engine RPM and watch for a change in the meter reading. Next, Tap on the sensor and observe any meter changes or fluctuations in engine RPM.
To replace your mass airflow sensor, the tools you will need include a regular screwdriver, a 1/4-inch drive socket set, standard or metric wrenches, possibly some Torx bits, and the correct mass airflow sensor for your vehicle. The first step whenever working on the electrical system is to turn off all the accessories, including the ignition key. If you are working in the area of the electric fan, make sure to disconnect the wire leading to it or remove its fuse from the fuse block. This will prevent the fan from starting up suddenly and causing physical injury. On many General Motors vehicles, the mass airflow sensor will be located in the air duct between the air cleaner and throttle body. Once the mass airflow sensor has been found, remove the harness connector. Note how it plugs into the sensor. This is important for correct installation of the new sensor. Inspect the harness connector for cracks in the wires or corrosion on the connector. If found, repair any broken wires and clean any corrosion from the terminals. Loosen the clamps securing the mass airflow sensor in the air duct, located between the air cleaner and throttle body, and move the clamps down the air duct hose. Remove any brackets or other mounting hardware as necessary. Separate the mass airflow sensor from the air ducts and remove the sensor from the vehicle. Save any mass airflow sensor to air duct seals if so equipped. Compare the old sensor to the new sensor to be sure of correct replacement. With the sensor removed, you can inspect the honeycomb for damage. If the honeycomb is scratched or damaged, a new sensor must be installed. Before installing the new sensor, inspect the air ducts for damage or possible restrictions. Replace the air ducting if damage is noticed. Reinstall any sensor to air duct seals on the new sensor. Position the new sensor into the air ducts, making sure the airflow directional arrow on the sensor is pointing towards the throttle body. Move the clamps to the ends of the new sensor and tighten them. Check to be sure the sensor to air cleaner connections are airtight or the sensor will not work properly. Carefully reconnect the harness connector lead into the new mass airflow sensor. Remove the air cleaner cover and inspect the air filter. If the filter is dirty, wet, or clogged, replace the air filter with a new one. Reinstall the air cleaner cover. Reconnect the electric fan connector or reinstall the fuse if earlier removed. On many late model General Motors vehicles, the mass airflow sensor will be attached to the throttle body itself. Just as earlier, turn off all interior electrical accessories and turn off the ignition key. Unclip and disconnect the harness connector. A small screwdriver may be useful to release the clip. Inspect the harness connector for cracks in the wires or corrosion in the connector. If found, repair any broken wires and clean any corrosion from the terminals. Remove and save the mounting screws. Match the old and new sensors to be sure of correct replacement. Install the new sensor and snug up the mounting screws, being careful not to over-tighten. Reconnect the harness connector onto the new sensor. Make certain it is fully seated in the sensor. Start the vehicle and allow it to idle until fully warm to verify correct mass airflow sensor operation. If the service engine soon or check engine light is lit on the dash, or the engine stalls or runs rough, turn the engine off and inspect the harness connector plug for correct installation.
Let's review how easy it is to replace a mass airflow sensor. First, turn off all the electrical accessories, including the ignition switch. Disconnect the electric fan connector or fuse. Locate the mass airflow sensor. Disconnect the mass airflow sensor electrical lead. Inspect the electrical lead for damage or corrosion. Remove the mass airflow sensor from the air duct system. Inspect the air ducts for damage and obstructions. Install the new sensor into the air ducts. Reconnect the electrical lead to the sensor and reconnect any other connections or fuses removed earlier. Inspect the air filter and replace it if necessary.
Okay, Jim, I've got a late model GM vehicle. We'll use that as our example. I'm driving down the road, down the highway as a matter of fact usually, and what happens is I step on the throttle and now I've got a bucking sensation, or it kind of hesitates as I'm going to take off. And I've also got an intermittent check engine light. What do you think?
Well, the fact that you've got a check engine light at all means you're going to have to pull the codes.
Okay, I've done that, and what I've come up with on my particular vehicle is a code 21. Where do we go from there?
Well, first of all, find what the code 21 means. You can refer to the manual that you use to work on the type of car that you have, such as this one.
Okay.
And in the code chart section of this book, we find a list of trouble codes. And code 21 in this case talks about a throttle position sensor problem.
Okay, so what we want to do then at that point in time is a quick 2-minute throttle position sensor test, and we'll show you how to do that right now. What we've got on the bench here is the throttle position sensor out of a carbureted vehicle. And really all a throttle position sensor is sort of like a rheostat, or your volume control knob on your stereo. As you push down on this volume control, it increases the resistance or decreases the resistance depending upon your vehicle, and changes the signal back to the computer. And it's got 3 wires that come out of it just like this. All TPSs have those 3 wires. Now testing it's easy.
It sure is. What we'll use is the ohm meter. And what I like to do is turn my ohm meter onto the 20,000 or the 20K scale, because that's a range that gives you a nice big spread of numbers when you're trying to test something that's going to cause numbers to change all the time.
Okay.
Now, since you have 3 terminals here in your throttle position sensor, and I only have 2 alligator clips, you have to remember which 2 to connect to. So take one lead, either the red or the black, it doesn't matter, and put it in the center of the 3.
Okay.
Then use your other lead to get into either one of the other 2 you want. So let's just do this one. Now we're connected to the center and the bottom terminal, and then we can observe the reading on the ohm meter.
Okay, what I'm going to do is actually press down on this little plunger here, and we're going to watch the reading on the ohm meter go up as I'm pushing down on the plunger. And we want to look for a real smooth transition of those numbers, and this one appears to be okay. You want to do that in both directions. Numbers will go up in one direction, back down in the other, and you want to do it relatively slow, because if you don't do it slowly, you could miss a bad spot in there.
You're right, and the important thing is the numbers should follow what you're doing. Nice and slow progression, up and down or down and up.
Okay, this one appears to be okay. So we've checked our throttle position sensor. That is okay. We've still got our code 21. Now where do we go?
Well, if that's the case, we know that there's something else wrong. So you can get into your manual such as this that talks about trouble codes and diagnostic trees, and we can actually find a diagnostic trees for code 21 and the throttle position sensor. So by following the step-by-step diagnostic tree, we're going to arrive at either a bad wire, a bad electrical connection, or maybe even a bad computer. But it's one of those things that's causing the problem on this vehicle.
Okay. Now, on the other hand, we've got another TPS here that we pulled off of a fuel-injected vehicle. Now, it looks a little bit different, but again, it's got our 3 terminal connectors on that. And why don't we run a test on this one, Jim, and see what we come up with here.
Once again, the ohm meter can be left in the 20,000 range, and take one lead, stick it in the center as you're doing,
okay,
and then you're free to put that one in either of the other 2 you want.
Okay.
And here we have...
Let me see, I got her on there now.
Good. And here we have a reading, so go ahead and operate it just as you did before, and we'll see how this one does.
And we're going up slowly along with my movement, and we'll see. There it is. There's our open circuit, and now look at our resistance is changing again. And
that's
we'll come up here, another open circuit.
That's quite erratic, isn't it?
Yeah, it sure is. So that's what's creating my bucking sensation when I'm trying to accelerate, and it's also giving me my check engine light, isn't it?
That's right. This is a bad one, and this is what it looks like. See, the ohm meter is picking up all those bad spots in there.
So hence the reason that you do want to perform this test very slowly, because if you don't perform the test slowly, you go too fast, you could zip right by those numbers and not actually even notice it at all.
Right. Replacing this part would solve your problem.
Sure. 2-minute test, you're down the road again.
Although there are many types of throttle position sensors, they can all be tested by the following procedure. Turn the ohm meter on to the appropriate scale and connect the meter leads to the throttle position sensor. Observe and record the meter reading. Sweep the throttle position sensor through its range of movement. Observe and compare the meter readings as the sensor is swept. If the sensor passes these tests, locate and follow a diagnostic chart for further tests.
Replacing the throttle position sensor, or TPS, on either carbureted or fuel-injected vehicles can be easy with the right tools and our help. There are several different styles of throttle position sensors in use today, but all will resemble one of the styles shown and will be replaced in a similar manner. The tools needed to replace the throttle position sensor on a fuel-injected vehicle include one or more of the following: a set of screwdrivers, a 1/4-inch drive socket set, a set of small Torx bits, and a 10 meg-ohm input digital volt ohm meter. In addition to those tools, you'll need the following to replace a TPS on a carbureted GM vehicle: a 3/32 drift punch, a hammer, a 5/64 drill bit, an electric drill, a number 8 sheet metal screw, a hex key wrench set, a tube of thread locker, a needle nose pliers, and a TPS adjusting tool. To prevent getting burned and to make the job easier, always begin repairs on a cool engine. The first step whenever working on the electrical system is to turn off all electrical accessories, including the ignition key. The first type of TPS we will replace is on a carbureted GM vehicle. Remove the air cleaner assembly to gain access to the carburetor where the TPS is located. Disconnect the MC solenoid and TPS electrical connectors from the carburetor. Disconnect the upper choke lever from the end of the choke shaft by removing the retaining screw. Remove the lever from the choke rod by rotating it until it disengages from the rod. Remove the choke rod from the lower lever inside the main body casting by holding the lower lever outwards with a small screwdriver and twisting the choke rod. Using a 3/32 drift punch and hammer, drive the accelerator pump lever pivot pin inward until the end of the pin is against the air horn. Lay the pump lever off to the side and out of the way, and using a needle nose pliers, remove the TPS plunger. Using a needle nose pliers, remove the vacuum hose from the choke pull-off. Now, remove the 2 front carburetor mounting bolts with the ratchet wrench and socket. Unscrew the center mounting stud for the air cleaner. Remove the air horn to main body screws. When removing the 2 countersunk screws located inside the air horn, use a magnetic screwdriver to prevent dropping them into the intake manifold. If you are uneasy about removing these screws with the carburetor on the engine, we suggest you stop here and remove the carburetor from the intake manifold before proceeding any farther. Remove the air horn from the main body by lifting it straight up and off. Pushing up from the bottom with a small screwdriver on the electrical connector, remove the TPS assembly from the main body. Using a needle nose pliers, retrieve the spring from the TPS well. Compare the old TPS with the new one to be sure of the correct replacement. Install the new TPS spring. Position the new TPS assembly into the carburetor main body. Be careful to align the groove in the electrical connector with the slot in the main body casting. Push down on the electrical connector and the sensor so the wires and the connector are below the main body casting surface. Reinstall the air horn gasket and air horn, holding down on the pump plunger assembly. To ease installation, insert a thin screwdriver between the air horn gasket and the main body to raise the TPS adjustment lever over the sensor. Loosely install all the air horn screws. Tighten the screws evenly, working from the center outward in a crisscross pattern. Reinstall the 2 front carburetor mounting bolts and tighten them securely. Reinstall the air cleaner mounting stud and tighten it hand tight.
reconnect the vacuum hose for the choke pull-off. Place the TPS plunger through the hole in the air horn and reposition the accelerator pump lever. Using a needle nose pliers or a small screwdriver between the pivot pin and the air horn, carefully pry the pivot pin back through the pump lever until it is flush with the housing. Using your hand, reinstall the choke rod into the lower choke lever by twisting slightly while holding the lever over with a small screwdriver. Install the upper choke lever back into the choke rod. Position the lever onto the end of the choke shaft, making sure the flats on the shaft align with the flats in the lever, and reinstall the retaining screw. When properly installed, the lever will point to the rear of the carburetor. Plug in the MC solenoid and TPS electrical connectors. The last step is to check the TPS adjustment. This step must be performed with a digital 10 megohm input voltmeter. In the appropriate service manual for your vehicle, or in the instructions included with the new throttle position sensor, locate the voltage specification. Then, back probe the center and lower terminals of the TPS connector as demonstrated. Set your voltmeter on the low voltage scale and connect the leads for your voltmeter to the back probe connectors. With the air conditioning off and the idle speed control plunger retracted, turn the ignition switch to the run position. Read the TPS voltage. Some vehicles, such as ours, will require it to be adjusted with the choke on the high step of the fast idle cam. If it is within specifications, you're done. If not, you must remove a small tamper-resistant plug that covers the TPS adjustment screw. To do so, drill a hole in the plug with a 5/64 drill bit. Be careful so as not to drill too far and damage the TPS adjustment screw. Insert the number 8 sheet metal screw in the hole drilled. Using a pliers, pull on the screw to remove the plug. Use a special TPS adjustment tool to bring the voltage within specifications. On our vehicle, the specification is 0.97 volts on the high step of the fast idle cam. Always make sure your final adjustment is made by turning the screw in a clockwise motion. Once adjusted, place a drop of thread locking compound in the adjustment hole and reinstall the new tamper-resistant plug supplied with the new TPS until it is flush with the boss on the carburetor. Remove your voltmeter and back probe pins and you're done. Replacing the throttle position sensor on fuel-injected vehicles is much easier. Remove whatever components are in the path of access to the TPS. Unplug the electrical connector from the old TPS. A small screwdriver may be used to ease the unlocking of the connector clip. Remove the screws that mount the TPS to the throttle shaft. Compare the old and new TPSs to be sure of the correct replacement. Install the new TPS using the screws removed earlier. Inspect the electrical connector for signs of broken or cracked wires or corrosion on the terminals. If any is found, repair connector or clean corrosion before reconnecting. Plug in the electrical connector, making sure it is fully seated in the TPS. Back probe the wires on the TPS just as during the carburetor type of replacement. Connect your digital voltmeter to the probes to check the adjustment. Turn the ignition key to the run position. Note the reading on the voltmeter. If it is within specifications, you're done. If not, simply loosen the mounting screws, reposition the TPS until voltage is within specifications, and retighten the screws. Test drive the vehicle once completed to be sure of correct installation.
To replace a throttle position sensor that is located in a carburetor, begin by turning off all the accessories, including the ignition switch. Remove the air cleaner assembly. Disconnect the mixture control solenoid and the throttle position sensor electrical leads. Disconnect and remove the choke linkage from the carburetor. Remove the accelerator pump lever and linkage. Next, remove the throttle position sensor plunger remove all vacuum lines connected to the top of the carburetor. Remove the 2 front mounting bolts. Next, remove the air cleaner mounting stud. Remove all the air horn screws. Lift the air horn up and away from the carburetor main body. Remove the old throttle position sensor and spring from the main body. Install the new spring and throttle position sensor into the carburetor. Next, reinstall the air horn gasket and the air horn. Start all of the air horn screws and tighten evenly. Reinstall and tighten the 2 front mounting bolts. Thread the air cleaner stud back into the carburetor. Reconnect all vacuum hoses. Next, reinstall the throttle position sensor plunger and the accelerator pump lever. Reinstall the choke linkage, making sure the choke lever points to the rear of the carburetor. Reconnect the mixture control solenoid and throttle position sensor electrical leads. Lastly, check the new throttle position sensor's adjustment using a digital voltmeter. Once the throttle position sensor has been replaced, the sensor may need to be adjusted. Let's review the steps involved in adjusting the sensor. First, locate the throttle position sensor voltage adjustment in a service manual or in the new sensor's instructions. Next, back probe the throttle position sensor's electrical connection. Connect the digital voltmeter to the back probe pins. Turn the ignition switch to the on position. Observe and compare the meter reading to the specification given. Remove the throttle position sensor adjustment plug. Adjust the sensor to the required specification. Using a liquid thread locker, install the new throttle position sensor adjustment plug. Lastly, remove the voltmeter leads and back probe pins from the electrical connection. To replace a throttle position sensor found on a fuel-injected vehicle, follow these steps. Remove the electrical connection from the throttle position sensor. Remove the mounting screws and the throttle position sensor from the throttle body. Install the new throttle position sensor. Inspect and reconnect the sensor's electrical lead. Back probe the throttle position sensor connector. Next, connect the voltmeter leads to the connector. Turn the ignition key to the on position. Observe and record the meter reading referring to a manual for specifications. Adjust the throttle position sensor until it falls within specifications.
Computer-controlled vehicles are equipped with a small motor used to help control idle speed, commonly called the ISC motor or idle speed control motor. Jim, when is the idle speed control motor actually used?
Well, like its name implies, Scott, it does control the idle speed. You have to do that sometimes, like whenever your air conditioner clutch cycles on when you're idling. Or perhaps you're idling for a long time at a traffic light and the engine starts to overheat or heat up. So the RPM would have to be raised to get coolant circulating.
Sure.
Sometimes power steering pressure reaches maximum effort one way or the other. This all gives extra demand on the motor, and this little thing right here will cause the idle speed to come up to compensate for these additional loads.
Okay, but actually they can be tested on or off the vehicle, and it's really not difficult at all.
Absolutely. When you get a trouble code for an idle speed control motor, generally it means that it's not working at all. And what you need to do is find out whether the motor itself is not working or whether something called the nose switch way out here in the front is not making contact.
Okay.
So this is a very simple two-part test. I like to use a battery to operate the motor itself. In fact, a 9-volt battery is one of the handiest things I've ever found, because if this motor will respond to a 9-volt battery, we know it will work flawlessly with a 12-volt battery that's on the car.
Certainly.
To test, you need to find the red and the black wires, which traditionally mean positive and negative in electronics, and connect those to your battery terminals. So as I connect the black lead to the negative battery terminal and the red one to the positive, it should extend the nose. And as you can see, it did that.
It sure does.
And to retract it, we simply reverse the connections on the battery and it should move in the opposite direction.
And it did, without
Now-
any binding.
Exactly. And without any binding, we know that this thing is clear. There's no nicks in the gears, and the motor, of course, is not damaged because it can actually work the mechanism.
Okay.
So, the nose switch then is the only other thing we need to be concerned with. And for that, I generally like to use an ohm meter. Now, the ohm meter can be attached across the other two leads. In this case, they are orange and purple. And I'll turn the ohm meter on, just most anywhere, down in the low range someplace. And that should, of course, supply us with some sort of a reading, showing continuity through the nose switch. Now, if you'll press that, the switch will open, and the reading will change to an open circuit.
Yep.
And every time you cycle that back and forth, it should change the meter reading.
And it does.
Now, General Motors idle speed control units work exactly the same way. They just have a different shape. Now, here you'll find that we do in fact have a nose switch, and we have terminals rather than wires.
Okay.
Now, these terminals are arranged this way. The two closest to the motor are for the motor. The two furthest away are for the nose switch. So normally I like to use my meter leads as all the test equipment. So since we're still connected to the meter,
Okay.
why don't we just go ahead and check the nose switch. So if you'd like to hold on to that, and I'll hold the meter, and we'll put these two leads into the terminals farthest away from the motor. Remember, those are the nose switch terminals. And we'll turn the meter on.
Okay.
And
we have actually an open circuit
An open
showing
circuit.
there. And now I'll push it in. You hear the switch click. And we show continuity one way, open circuit the other way.
Right, so now we know that nose switch works.
Certainly.
All we'll have to do now is test the motor. I'm going to take the leads right off of the ohm meter and use them for jumper wires.
Okay.
That way, we can use the same probes in the other two connectors, the two that are for the motor. And that gives us a real nice way to connect up. And then we'll use the other ends, of course, to connect up to the battery. And as I connect one lead to this terminal and the other to that, you can see how
Okay.
the motor moves out. And it should retract when I reverse the leads.
And it does, without binding. So,
Right. So this is a simple test that they can do. You can do at home in order to test your idle speed control motors.
and one last point, you can do that on the vehicle or with the component off from the vehicle.
Let's look at how easy it is to test an idle speed control motor. Connect the idle speed control electrical leads to a test battery. Observe the nose switch movement and the idle speed control motor sound. Reverse the electrical connections and observe the idle speed control nose movement. Connect the ohm meter leads to the idle speed control motor and set the meter to the appropriate scale. Observe the meter reading. Depress the nose switch and observe the meter reading.
To replace your idle speed control motor, the tools you will need include a set of screwdrivers, a pair of pliers, a 1/4-inch drive socket set, some masking tape and a marker, a tape measure, the proper service manual, and the correct idle speed control motor for your vehicle. Before beginning any repairs under the hood, always begin with a cool engine. The first step whenever working on the electrical system is to turn off all electrical accessories, including the ignition key. Idle speed control motors are attached to the carburetor. Begin by removing the air cleaner housing cover. Mark all hoses and wiring connections going to the air cleaner housing and remove the housing from the carburetor. Locate the idle speed control motor and disconnect the 4-terminal connector. A small screwdriver may be useful to help release the locking clip on the connector. Using a pair of pliers, remove the throttle return spring from the idle speed control bracket. Remove any mounting screws from the idle speed control bracket and remove the idle speed control motor and bracket from the carburetor. Compare the old idle speed control motor and bracket to the new one to be sure it is the correct replacement. If the old bracket differs from the new one, remove any mounting screws from both brackets and install the old bracket onto the new idle speed control motor. Next, you need to adjust the plunger on the new motor. Distance A, as shown in this illustration, needs to be determined. Measure the distance between the end of the plunger and motor housing on the old idle speed control motor. This is distance A. Now measure distance A found on the new idle speed control motor. If the distance measured from the new motor is different than that on the old motor, adjust the plunger on the new motor to match distance A found on the old motor. Then, using the mounting screws removed earlier, reinstall the new idle speed control motor onto the carburetor. Carefully reconnect the electrical connection on the motor, making sure it is fully seated. Once the new idle speed control motor has been installed, a base and extended RPM speed check must be performed and adjustments must be made. Please refer to an automotive service manual for the correct service procedure and idle specifications on your particular vehicle. Now reinstall the throttle return spring to the same position as removed earlier. Reinstall the air cleaner housing and reconnect any hoses earlier disconnected. That's all it takes to replace an idle speed control motor.
Replacing the idle speed control motor is an easy job. Let's look at the steps involved. Turn off the electrical accessories, including the ignition key. Remove the air cleaner assembly. Locate the idle speed control motor. Disconnect the electrical lead from the motor. Remove the throttle return springs from the idle speed control bracket. Next, remove the mounting screws and assembly from the carburetor. Adjust the plunger length of the new idle speed control motor to match the old motor. Install the new idle speed control motor and bracket onto the carburetor. Next, reconnect the electrical lead. Refer to a service manual and perform an RPM speed check on the new motor. Reinstall any throttle return springs. Lastly, reinstall the air cleaner assembly to complete the replacement.
With the advent of computerized vehicles, they've got a lot of input sensors that send signals to the computer so it can control the operation of the engine. One of the sensors that they've recently added is knock sensors. And I'm holding a typical knock sensor right here. And what that does is it actually senses knocking or pinging that quite often happens with the higher operating temperatures and lower grade fuels that are being used in the vehicles today. And Jim Bates is with us to tell us a little bit more about it and show us a quick and easy test to tell if it's good or bad. Jim, first off, where do they commonly put knock sensors in a vehicle?
Well, basically you'd find these things in the cylinder head near the rear of the engine, or sometimes in the intake manifold where a Y would be.
Okay.
And in those locations, it can pick up the vibrations that knocking produces. And so when the engine does start to knock or ping, these vibrations will cause the device inside the sensor to produce a small millivoltage, which the computer will pick up, and it knows it's time to retard the timing.
Okay.
So to test something like this, all we have to do is measure or record that millivoltage. Testing can be done on or off the vehicle.
Sure.
We're doing it, of course, off the vehicle, so we'll hold it in our hands and connect this device, which I brought along with me.
Okay.
And it has two leads, which we simply connect to the sensor. I'll connect one up here and the other one down at the bottom. And the little LED here should flash every time knocking hits this sensor.
Okay.
And we'll substitute the engine knocking with a metallic object. I'll just use the side cutter here. And every time I hit that, the light should flash.
Okay. You bet.
So we can see that this sensor is indeed working.
Certainly. And what we have here on the other end of the lead is obviously it's just a 12-volt source that is connected to a 110 power supply, but you could use the vehicle's car battery to do the same test.
Exactly.
And about the only thing that you're going to notice if your knock sensor has gone bad is probably excessive pinging.
Excessive
right?
pinging.
Okay. Well, that's all it takes to test a knock sensor.
Testing a knock sensor is very simple and requires only the following two steps. First, connect the tester leads to the knock sensor and a 12-volt power source. Then, tap on the sensor with a metal object and observe the tester light.
To replace your knock sensor, the tools you will need include a regular blade screwdriver, a standard or metric wrench set, a torque wrench, a standard or metric socket set, and the correct knock sensor for your vehicle. To prevent burns on your hands, always begin repairs with a cool engine. The first step whenever working on the electrical system is to turn off all electrical accessories, including the ignition key. Locate the knock sensor. Depending on the type of vehicle, it will be located on the side or top of the engine block. Let's look at the removal and replacement of the knock sensor. On many vehicles, it may be necessary to remove components or the air duct, as in the case of this vehicle, in order to gain access to the sensor. Disconnect the wiring harness connector from the knock sensor. Using the proper wrench or socket, remove the knock sensor from the engine block. Because some knock sensors are located in the engine block, some vehicles may require the radiator coolant to be drained. Compare the old knock sensor to the new one to be sure it is the correct replacement. The new knock sensor will have a special coating on the threads. Do not remove this coating. Reinstall the new knock sensor, starting it in the threads by hand to prevent cross-threading. For proper operation, the new knock sensor must be correctly tightened. Using a torque wrench, tighten the new sensor to 14 foot-pounds. If the sensor is tightened too tight, it will be too sensitive. On the other hand, if the sensor is stalled too loose, it may not work properly at all. Before attaching the wiring harness connector, inspect it for signs of corrosion and any loose or broken wires. Clean and repair any damaged wires found. Reconnect the wiring harness connector onto the new knock sensor, making sure it is seated fully in place. Reinstall any components or air duct earlier removed, and you're done.
Let's review how easy it is to replace a knock sensor. Begin by turning off all the electrical accessories, including the ignition switch. Next, locate the knock sensor on the vehicle. Disconnect the sensor's electrical lead. Then, remove the sensor from the engine. Install the new knock sensor in the engine hand tight. Torque the sensor to the proper specification. Finally, inspect the sensor electrical lead and reinstall.